Hello everyone, this is my first attempt at a video, so we're going to try to iron out some wrinkles as we go along. Please bear with me. I only have 15 minutes to record, so I'm going to be working through examples maybe quickly, but you can always have the opportunity to pause, rewatch, and maybe even try examples before I go over them. We're going to begin today's lesson by going over the logarithm, which is what we went over last class. And up at the top of your screen, there's a definition for the logarithm. It says a logarithm is an exponent. The expression log base a of x represents the exponent to which the base must be raised in order to obtain x. So essentially here we're saying that this expression represents the exponent to which the base, so this base is a, what that has to be raised to get x. So the base of your log is the same thing as the base of your exponent. The a and a are the same. So if my exponent is a, the base is a. We're trying to figure out what it needs to be raised to. So that's what it's equal to up here. It's equal to some expression or some variable or some number. In this case, it's y. So a to the y is, we're trying to figure out what gives us x. So we just can move back and forth along this logarithmic function. Below there's a graphical representation. Up top we have a line that represents f of x is equal to 2 to the x power. Below we're going to graph its inverse function, and we did this in class, but the inverse function I believe has the points, right about here. So we come up and it's asymptotic to the y-axis, and we come up and we're going to sketch the curve. It looks something like this. So this is the graph that if we flipped it over the line y equals x, which is the red line right here, y equals x, we're going to get this graph. And this graph is just log base 2 of x. And so log base 2 of x and 2 to the x power are the inverse functions. Right here we have an example where we wanted to move from a exponential function to a log-based function, and we have our rule to the right. We have if y is equal to log base a of x, if and only if x is equal to a to the y power. So we're going to look at our exponent, and we're going to ask ourselves, what is our base? Well, our base is 5, so the base of our log is also going to be 5, right? And then this is going to be equal to the exponent we have to raise 5 to. So this is equal to -3. And then we're just taking the log of whatever our expression was originally equal to, which is 1 over 125. So we can move between an exponential function and a log function with relative ease. And hopefully by the end of this lesson, it'll be even a little bit easier. So again, I encourage you to pause the video at this time and maybe try this example on your own. I want you to rewrite this expression, this exponential expression, in logarithmic form. So go ahead and pause the video and try it, and we should be back and we should have an answer. We're going to approach this the same way. Log of 16, because again, the base of our exponent is 16, so it's log base 16, is equal to the exponent, in this case is -2, and we're taking that of the expression 1 over 256. So hopefully, again, you were able to get this answer, and we're going to move on, making good time so far. So we don't just have to move, like from this example, we move from exponential to logarithmic. We can also move from logarithmic to exponential. So if we have a logarithmic function and we want to move to an exponential function, we go about it the same way. The base of our log is still the same base of our exponent, and it's going to be raised, it has to be raised to some exponent. That's what the log is equal to. It's raised to -3, right? So that's going to be equal to, again, what we're taking the log of, and in this case, we're taking the log of 164. So you can go back and forth as much as you need to. Again, at any point, if you're just a little stuck, you can go back and rewatch the video, and if it's still not adequate support, I'm always here. If you need any questions, you can always email me or see me in class or after school. So this way that we're doing this might be a little bit confusing. I'm going to introduce a new way to think about solving these log problems that might be a little bit easier for some people. and the term is going to be exponentiating. And I like this exponentiating. And this is kind of asking yourself, if we're solving a two-step equation, x plus 2 is equal to 10, well, to solve this, you have to do the inverse operation of adding 2, which is subtracting 2, right? And the same thing for multiplication and division, and square roots and squares. In this case, for exponentiating, in order to kind of think about this algebraically, the inverse operation of a log is an exponent, right? So instead of taking log base 9 of 81, we can raise both sides to the 9th power. So if I raise this to the 9th power and I raise this to the 9th power, so just to rewrite this so it might look a little less confusing, we're going to have 9 raised to the log base 9 of 81 is equal to 9 to the 2nd power. Now, the reason we do this is just like addition and subtraction, or multiplication and division, exponents and logs cancel each other out. So if you have an exponent with the same base of the log, these two things will just cancel each other out. So you're left with just 81, which is no longer going to be an exponent. It's going to drop down to just a whole number status. You're going to have 81 is equal to 9 squared, which, hey, what we know about 9 squared, that should be pretty obvious, right? So this is a new method that we're going to kind of try to implement, especially when we get some crazy variables in our problems to do. So we're going to practice again with some low numbers. And you can always check any of these answers in your calculator. So if you would like to try the next example on your own, I encourage you to pause the video and do it. And if you've taken the time to pause the video, you could be back now. And we're going to look, we have log base 1/12. So that since the log has a base of 1/12, the exponent has to have a base of 1/12. So I'm going to raise both sides. I'm going to have 1/12 raised to this power and 1/12 raised to the 2nd power. Okay? So again, since I have, essentially, I'm just going to write this out so we can visually see it. 1/12 raised to the log base 1/12 of 1 over 144 is equal to 1/12 raised to the 2nd power. Again, just like before, since our log has the same base as our exponent, these two things cancel each other out, and we're left just with what was left inside of the log. So our final answer might look like this. 1 over 144 is equal to 1/12 squared. Right? And again, this should look pretty right because 1 squared is 1, and 1 squared is 1, and 12 squared is 144. So again, that should be making a whole lot of sense, hopefully. If we're moving on, we can try to do this with more types of equations. Again, if you think you have the ability, I encourage you to pause before each one of my examples so that you can try it yourself. If we're looking at this example, and if you've unpaused already, you should see that we have a log base of 7. So we're going to have 7 raised to these powers and 7 raised to this power. So 7 raised to log base 7 and 7 raised to the 3rd power. So 7 raised to log base 7 is going to cancel, and we're going to be left just with x is equal to 7 to the 3rd power. And this is something you could do in your calculator. 7 cubed is 7 times 7 times 7. And just for the sake of time, I have a calculator right here. 7 cubed is equal to 343. Again, you could always, if you just want some reassurance, you could plug this back into your original equation once we learn how to solve this in the calculator, and it should give you your correct answer. But your final answer here is x, again, is equal to 343. So at this point, maybe try to pause the video and try the next example on your own. So if we're trying the next example on our own, we have a log base 4. That means we're going to take the 4th power and raise each side of our equation 4 to this power and 4 to this power. So the 4's will cancel. The exponent and the log will cancel. We're left with x squared is equal to 4 cubed. And in this case, we know that x squared 4 cubed is going to be equal to 64. And we can continue solving this just by taking the square root. And x, whenever we take the square root, we have a plus or minus. X is equal to plus or minus 8. Make sure you have that plus or minus there. All right? So I'm going to pause the video to see where this is at, because I have to go to a quick meeting. So hopefully this doesn't mess anything up. Okay, so we're back, and we're going to try this other example. Again, I encourage you to pause the video and attempt to do it yourself before we begin. All right? But with this example, now we have an exponent raised to a power is equal to a number. So we need to somehow get rid of this exponent. And to get rid of this exponent, it's still going to be called exponentiating, but we're going to be doing, instead of what we did last time, where we raised each thing to the whatever power the base was of the log, we're going to be taking a log with the base of the exponent of each side. So we take log base 5 of both of these sides. Now this is going to cancel this. We're going to have x plus 3 is equal to log base 5 of 615. Well, now we run into another problem, because we have to find out a way to evaluate log base 5 of 615. If we look at our calculator to the right, we have a log key here, but this log key uses log base 10. So in order to get to log base 5, we have to use something called the change of base formula, which is written below. And the change of base formula says that if we have log base a is equal to x, then all we have to do is take the log with some common base of x is divided by the log of the same common base of what the base was previously. So the good thing is we have two default logs in our calculator. We have log, which is log base 10, and ln, which is log base e, which we'll learn about in maybe our next slide if we have time. If we're following this formula, in this case, if we're following the formula, the log base b would be, if we're using this log key, would be base 10, or if we're using this log key, the natural log would be base e. Either one will work. So if we're trying to evaluate this right here, we're going to be taking log base 10, which is again just a regular log key in the calculator, of 615 divided by log base 10, which again is the regular log in the calculator, of 5, because that's our previous base. And this is going to give us a number. If we type this into our TI-84, which is absent at the moment, let me grab one real quick. Log of 615 divided by the log of 5 is equal to 3.989998. And I just ended it kind of at an arbitrary decimal place. Usually we want to try to keep it to 3 decimal places, but for this example, we'll just do it here. So now I have 3, and I'll truncate this to 3 decimal places. We'll round that up. 3.990 is equal to x plus 3. And to finish the problem, what you're going to do is subtract 3. And x is going to be equal to, or approximately equal to, in this case, 0.99. Okay? And we have about a minute and a half left. So in this minute and a half, we're just going to quickly explain the natural logarithm. The natural logarithm is when we're using e. E is just a naturally occurring number. It's something that occurs frequently, and I'm trying to do this in less than a minute now. It's approximately equal to 2.718281828, and it keeps going on forever. Just like pi, it's an irrational number. It's non-terminating, non-repeating, and it's going to keep on going forever. And when we have log base e of x, we instead write, because it's so naturally occurring, we write ln of x. And ln just means natural log. These two things, at log base e and natural log, are literally the same thing. So we can, when you see e, it's just a number. So if I have e to the x is equal to 7, and I wanted to solve this problem, we could just simply take the natural log, or ln, of both sides, just like we were exponentiating it. To cancel that, we had x is equal to ln of 7. So there's your quick 15-minute lesson. Hope this is beneficial.